proof by deduction. So this is when we're given like an hypothesis, a starting point, and we just want to do mathematics to show like, okay, this thing applies to the next step, and that step applies to the next step, and that step applies to the next step, until we get to our conclusion. This is called a proof by deduction. Sometimes called a left to right proof. Because you're literally starting at the start, and you're trying to get to the end by just following the chain of events. So, a proof by deduction. So let's start here. Our first example. Prove by deduction if x is less than -5, then x squared is greater than 25. So if we're going to start there, so we're going to start with the if x is less than -5. So usually we have to think about this. Okay, so I know x is less than -5. I want to show x squared is greater than 25. So I'm going to do some scratch work. This is just me thinking. So if we have x is less than -5 and I square both sides, I'll get x squared is less than 25. That's not what we're trying to prove. We're trying to prove x squared is greater than 25. And let's see if it makes sense, right? I think it makes sense, right? So let's pick a number that's less than 5, and then what happens when we square it, right? So like -6 is less than -5. If I square both sides, I get 36 is greater than 25, right? So it should follow. So the key to this is actually a little tricky. You understand the thing I did here, right? -6 is less than -5. But if I take the absolute value of both sides, then we switch it. So because if x is less than -5, then these are all numbers that are since like you're thinking about a number line. All the numbers on the left of -5, the numbers less than -5, all these numbers, they're all bigger than positive. When you take the absolute value of both of them, then it switches it. These are all bigger than 5. So then the absolute value of x is greater than 5. So when you do a proof, you're supposed to give like a reason for that. Like why do you go from here to here? Like how did that happen? So for us, it's just a geometric definition of absolute value. Now I don't expect everybody to know that right off the top of their head, but like the idea, like this is why it's a definition of absolute value. Might even say, like, oh yeah, these numbers are bigger than that number. And now we can just square both sides. So this is where, like, if you do proofs from college, you're like, okay, you're not supposed to use then and then again. Everyone wants to just do like then. So you can probably say like therefore, with a little like that, right? If I square both sides, I get x squared is greater than 25, which I was trying to show. QED. That means you're done in math proof talk. Right, but that's the idea, is like all these numbers are bigger than -5. Well, they're smaller, but when you take rid of the negatives, then these numbers are actually bigger than that. So how do you take rid of the negatives? You take the absolute value. So the absolute value of this guy must be bigger than the absolute value of that guy. So I get this, and then you square both sides, and you get the right answer. B, explain why the converse is not true. So when you try to show something is not true, it's not a proof, you can explain it, or you just do a counterexample. So the converse of this says x squared greater than 25 implies that x is less than -5. So again, look what you gotta think when we do these. We gotta think, what is this telling me? So they're saying that some number that means squared is bigger than 25. So like 7. Like what if x is 7? Right? 7 squared is bigger than 25. Does that imply that 7 is less than -5? And that is not the case. So like that's like counterexample. What if x is 7? Well, 7 squared would be greater than 25, but 7 is actually greater than, not less than -5. That's how these implications work, right? The first part has to be true. So like over here we said, oh, what if x is less than -5? And I said -6. -6 is less than -5, but then when I squared it, I guess that did work. When we try to do the converse, you pick any number that's greater than, when you squared it's greater than 25, it didn't work. So that's why this one's false. Okay, let's see. Prove the sum of 3 consecutive integers is divisible by 3. So 3 consecutive integers. So hopefully you did this a little bit in like IM1 or 2 or a class before. 3 consecutive integers we know as generally go as x, x plus 1, and x plus 2. Now you can play around with that a bit. I guess you do x minus 1, x plus 1. But this is generally 3 consecutive integers are x plus 1, x plus 2, or n plus 1, n plus 2. So there's my 3 consecutive integers. What do they want me to do with it? Prove the sum of them is divisible by 3. So we just want to add them. Sum means that. So we're going to go x plus 1 plus x plus 2 is divisible by 3. We'll get to that in a second. So we're going to start there. That's an imply that, or say then. So, and then we have, let's add up like terms, 3x plus 3. And then divisible by 3 means, well, can I factor it? Therefore, 3x plus 1. So this right here is something that's divisible by 3. So like that's kind of, honestly, it's kind of my scratch work. You're supposed to make it look nicer than that. So I'll probably do something like let 3 consecutive numbers, like let 3 consecutive numbers, whoops. Numbers be x plus 1, x plus 2. Right, so you want to give it like, okay, what are we doing? We're starting with this. We're going to start with 3 consecutive numbers. Right, and then we're going to show the steps to prove that when I add them, it's something divisible by 3, which just means that it's like you could factor out of 3. That's when something's divisible by 3, you can factor out of 3. So you just want to start here and get here. So next I'm just going to say, okay, so there's sum. So their sum is x plus 1 plus x plus 2. And then I'm just going to do the math. I'm going to like that equals, right, out of like terms, 3x plus 3, which equals, factor out the 3. 3 times x plus 1. Right, so like this implies that, which implies that. Or equals that, which equals that. So we showed it. We showed like if I had 3 consecutive integers, that when I add them, I get this, which equals this, which equals that. So I'm just going to end it with thus, the sum of 3 consecutive integers is divisible by 3. QED. So there we go. Last one. The following proofs by deduction are incorrect. Identify the incorrect steps in each case. So I just want to know what happened here. So this is incorrect. So they have 4x squared equals 3x, and then they have 4x plus equals 3, then they have x equals 3 fourths. I'll say from here to here, no problem. You can divide by 4. Problem is here. You can't divide by x. Because x might be 0. That's the rule. Can't divide by x. Because x might be 0, and you cannot divide by 0. And you can't divide by 0. So that's what happened here. You can't, it's one of the fatal mistakes. You can't ever divide by x, because it might be 0. Unless they tell you x is not 0. The next one, well hopefully everybody notices what's wrong here. Look at that. They split it. You can only split it when it equals 0, not when it equals a number. So this is the mistake there. Can only split when equal to 0. That's called the zero product property. Anyway, that's the lesson.